but a few minutes ago I had a problem with it. So we have May 28, right? May 28. All right, so again, we're going to look at section 4.4, harmonic motion. And let me zoom in so that you can see better. Okay, so 4.4 continued. I'm going to write down the differential equation x double prime plus 2c x prime plus omega sub 0 squared x equals to 0. So there is no forcing term here. There is no force applied to the system, but we do have damping. So C is not 0 in this case. So if we construct the characteristic equation, it will look like this: lambda squared plus 2c lambda plus omega sub 0 squared equals to 0, which is a quadratic equation, right? From this, we can find two characteristic numbers. So lambda sub 1 is going to be, using the quadratic formula, negative c plus, well, in this case, plus square root c squared minus omega sub 0 squared. Lambda sub 2 is very similar. Instead of plus, we will have minus, right? So c squared minus omega sub 0 squared. This is using quadratic formula. So from here, we have three cases. I remember I mentioned them, but we didn't do too many details. So case one. This is the case when C, the damping constant, is less than the natural frequency of the system, omega sub 0. So this case is called the underdamped case. The underdamped case. So in this case, the roots are distinct complex numbers. So we're getting C is less than omega sub 0 means you have square root of something negative, right? You have negative quantity under the square root, and that implies you have complex characteristic numbers. So if that happens, you have your solution x of t equals e negative ct. C is the real part, right? Negative c is the real part. And then inside parentheses, c sub 1 cosine of omega t plus c sub 2 sine of omega t. So here omega is square root natural frequency squared minus c squared. So again, this is case number one, underdamped case. So if your case is case number one, the underdamped case, then you should expect a few oscillations in the system. All right. Are there any questions so far? Any questions? Perfect. Let's move on to case number 2.
I have a quick little question.
Sure. What's the question?
So in your omega equals omega squared minus c, which c value are you using for that?
C is the damping constant.
Okay.
C is the damping constant, and omega sub 0 is our natural frequency of the system. So yeah, this is spring mass system, right? So we have a mass attached to the spring, and in this case, our spring mass system is going to oscillate. Eventually, oscillations will die out, of course, because you have e to the negative c times t. So this is exponentially decreasing function. So we expect our oscillations to eventually die out. So any other questions? So these constants c sub 1 and c sub 2, those are determined using the initial conditions normally. And this c here is the damping constant. Okay, so case number.
Actually, Professor, the W equals W naught squared minus C squared.
Yes.
Is that not supposed to be reversed because up top it's C squared minus W naught squared?
No, actually it's correct because remember this.
Huh?
Yeah. The reason for this is that this quantity under the square root is negative. So when you take square root of a negative number, let me show you some examples. So let's say, let me do this here aside on the separate piece of paper. So let's say your lambda is, I'm just making up numbers, -5, plus or minus square root, and under the root you have 25 minus something bigger, let's say minus 36, right? So in that case, you will have -5 plus minus square root -1 times 36 minus 25, and then you get -5 plus minus square root of -1 times square root of 11. Am I correct? This is 11. So in other words, you have to switch the order of subtraction. Square root of -1 will give you I, right? -5 plus minus, this is I, times, and under the root, this 11 is, you obtain it from changing order of subtraction, 36 minus 25.
Okay, that makes sense.
Yeah, so that's why when you look here, this omega over here, the subtraction happens in the opposite order. It's not c squared minus omega sub 0 squared, it's the other way, omega sub 0 squared minus c squared. So again, this is because you're getting complex characteristic numbers. So just like in this example, this quantity under the root is negative. So you factor out -1, inside parentheses, you're getting 36 minus 25, right? And then take square root of each factor, you're getting complex number I, and then square root 36 minus 25.
Okay, yeah, that makes sense.
Excellent, very good. So let me put this here, and I'll continue with case number 2. Case number 2 is overdamped case. This is the case when the damping constant is bigger than the natural frequency omega sub 0. So that means we're getting real, right? Real characteristic numbers because this difference is positive now. So we're getting two real distinct numbers. This is the overdamped case. This is the overdamped case. So we have the roots are distinct and real. So we have x of t equals c sub 1 times e to the lambda sub 1 t, and then plus c sub 2 e lambda sub 2 t. So again, two distinct real numbers, two distinct real roots. Okay, so So let us continue with the last case, case number 3. This one is critically damped case, C equals natural frequency. So we have, this is the critically damped case. This is the critically damped case. So in this case, we're getting one repeated root, right? So this square root is 0 because these two are equal. So we get square root of 0, and we're getting the same root repeated twice. In that case, x of t equals c sub 1 e to the negative ct plus c sub 2 times t e negative ct. So in case 3, you can see again we have exponentially decreasing terms here, and in case number 2, let's see. Well, it says overdamped case, so we cannot expect any serious oscillation. The oscillation is probably going to die. Let's see. Yeah, the oscillation is going to die. What just happened? I'm not sure what happened just now, but my iPad started to talk. I apologize. So yeah, I'm not sure why my iPad started to talk for no reason. Are you with me?
Yes.
Excellent. I apologize. So I want to add a note here. So in case 2, you can see you have exponential term. The first term is exponential, and the second, it's very important to observe. We don't expect here to have any serious oscillations, right? The reason is that both of these two characteristic numbers are negative. So lambda, so in case 2, lambda sub 1 and lambda sub 2 are both negative, okay? You can look back here. So lambda sub 1 is negative c, this is a negative constant, plus something less than c, right? Because c squared minus natural frequency squared. So under the square root, you have something less than c. So if you add negative c plus something less than c, you're getting negative lambda sub 1. Does it make sense?
Yeah.
Excellent. And in this case, it's even more negative, right? Lambda sub 2 is even more negative. So they're both negative. Therefore, our x of t, the function that describes displacement of the mass, this function is clearly going to 0 very fast. Both characteristic numbers are negative. So we expect in all 3 cases, oscillations are going to die out. But the fastest case is case number 2. This is where oscillations will die out faster than in any other case. So any questions? Any questions? So let me give you an example of a typical problem. This is from my old quiz from previous quarter. So, so last quarter, I gave the following problem on quiz number 4. So it was y double prime plus 3.2 plus 42.25 y equals 0. So again, this comes from an old quiz from last quarter. So our job is to find out if this equation represents underdamped, overdamped, or critically damped harmonic motion. So again, we have to decide which case is this, case 1, case 2, or case 3. All right? So this problem is actually very straightforward. We have to find C, and we have to find omega sub 0. Once you have those two numbers, all you have to do is to compare them. So tell me, what is C in our problem here? What is C?
3.2.
Well, 3.2 is 2C. Remember this equation here. So the number in front of first derivative is twice C. So 2C equals 3.2, which implies C equals 1.6. Am I correct?
Yes.
Excellent. And let's find omega sub 0. So omega sub 0 is going to be square root of 42.25. Am I right? So I'm taking square root of 42.25 and I'm getting 6.5. So now let's compare which is bigger, C or natural frequency?
The natural frequency.
That's right, natural frequency is clearly bigger. So C is less than the natural frequency. Therefore, this is case number 1, the underdamped case, right? So therefore, this harmonic motion is underdamped. Underdamped. Are there any questions here? Let's do one more. Again, this is from an old quiz. We have y double prime plus 19.4y plus 42.25 equals 0. Y is missing, y, right? 42.25y equals 0. So again, we have to answer exactly the same question. Is this harmonic motion underdamped, overdamped, or critically damped?
Shouldn't there be a y prime?
Yes, there should be y prime. I apologize. Yes, should be y prime. And here should be y. Excellent. So let's find C. Let's find C. So C, I will start by writing 2C equals 19.4, right? 19.4. From this, we're getting C equals 9.7. Am I right? 9.7. So this is the damping constant. So omega sub 0 is going to be exactly the same as before because we have exactly the same number here, square root 42.25. This one is, we said it's 6.5, 6.5. So which case is this one?
Overdamped.
Overdamped, very good. C is greater than the natural frequency. So C is bigger this time. And this harmonic motion is overdamped, overdamped. So any questions? Any questions? So this question is a good one to test knowledge of the definition, right? Definition of underdamped, overdamped, or critically damped case. So again, any questions? Any questions? All right, so this is all I wanted to discuss in this section 4.4. So 4.4, we covered all the basic definitions and we had examples. So did you try homework? Did you try homework? Do you have any questions on your homework? Let me ask you first, did I assign any homework on 4.4?
Yeah, I had a question for 4.4.
Sure, which one?
Number 1.
Okay, let's take a look. Number 1. All right, so we will do number 1. This is y equals cosine 2t plus sine of 2t. This is given. We will have to place the solution in the form y equals a cosine of omega t minus phi and compare the graph of your answer with the plot found in part I. So part I, you don't have to really worry about part I, even though you can graph this using Desmos. So let me, so let's first find A, the amplitude, right? Do you remember how to find amplitude? So we had formulas. C sub 1 squared, right? Plus?
Yeah, plus C sub 2 squared.
Excellent. Can you tell me what are your C sub 1 and C sub 2?
It's 1 and 1.
Excellent. That's correct. So those are ones. We usually do not write ones, but that's what we have. So C sub 1 is 1. C sub 2 is also 1. So we end up with A equals square root of 2. Square root of 2. So this is the amplitude. So to find omega, right? To find omega, we will have to, so I'm assuming you already have everything on your index cards, right? All these formulas, some of them are tedious. So omega is supposed to be actually omega sub 0. Omega sub 0 is the number in front of t. Am I correct?
Yes.
So this number right here, this is your natural frequency of the system. So this is equal to 2. And this should have omega sub 0 here. I don't know why the question has only omega. It should be omega sub 0. And finally, let's find phi. So phi, you have to choose the correct formula. Again, I hope it's on your index card. You should be using those often to get comfortable. So it's arctangent. You C sub 2 is positive and C sub 1 is positive, both of them. So we will have to use the first arctangent of B over A in the textbook is the same as C sub 2. Let me double check. C sub 2 over C sub 1. So arctangent 1 divided by 1. Arctangent of 1 is it pi over 4?
Yeah.
Excellent. So it looks like we found all the components. We're ready to say our y can be written in equivalent form, square root of 2 times cosine. Inside parentheses, we have the natural frequency is equal to 2t minus pi over 4. So we have our form, which is equivalent to what we had here originally. So we can also graph it using Desmos, right? If we want to double check, so we can, let's say, go here. Let me start a new tab. So I'm going to type Desmos and go to graphing calculator. Let's type y, let's call it f of t, right, equals. So I'm typing cosine of 2t, oops. Then we have plus sine of 2t. So you can see an oscillating function right here. Let me also do g of t equals square root of 2 times cosine, and inside parentheses we have 2 times t subtract pi over 4 and close parentheses. So you can see the two curves coincide, right? They are identical. So the red one and the blue one, they are exactly the same. So we can have peace of mind because they are supposed to be the same if you graph them, okay? So any questions?
Yes, I have a question.
Yeah, what's the question?
To get W sub 0, do you just square A?
W sub 0. To find it, we have to look at the number in front of t.
Oh.
So this number here in front of t, or here, right, the same thing. This number is W sub 0. I'm sorry, not W, it's actually omega, right? Omega sub 0.
Thank you.
Excellent. So any other questions? Please let me know. Any other questions? Perfect. Let's so let's take a look at inhomogeneous problems now. So we will discuss, this is section 4.5, inhomogeneous equations. There are two methods that we will discuss in this class, two methods of solving inhomogeneous problems. So let me first write down the DE. So this is inhomogeneous, right? Because we have a forcing term present on the right-hand side. P and Q have to be constants. Otherwise, the method will not work. So to find solution of such an equation, we have to do two things. First, we have to solve homogeneous problem. And then we will have to find particular solution of the non-homogeneous problem. And finally, add them together. So let me write this as the theorem. This is theorem 5.2. We're going to write it down and then we'll use it. So suppose y sub p is a particular solution, is a particular solution to the inhomogeneous equation, y double prime plus py prime plus qy equals f. Also, y sub 1 and y sub 2 form a fundamental set of solutions to the homogeneous equation. So let y sub 1 and y sub 2 form a fundamental set, of solutions to the homogeneous equation. Okay, so if you know those components, particular solution of the inhomogeneous problem and fundamental solutions to the homogeneous equation, we're done. We have solution to this entire equation. So it's going to be y of t general solution equals y particular plus linear combination of y sub 1 and y sub 2. So this is how we solve inhomogeneous problems. So we will use this theorem in section 4.5. Or this is the only theorem we're going to use in this particular section. So let's consider an example. Maybe we can, let's see, choose 5.6, example 5.6. So in this example, we have inhomogeneous problem, y double prime minus y prime minus 2y equals 2e to the negative 2t. So the question is, find the particular solution. Find a particular solution. All right, so this is the most difficult part of the problem, how to find a particular solution. So usually we look at the right-hand side, the forcing term. So this function f right here, function f. So this function determines which method to use to solve this equation. So in this case, we have exponential function. What happens if you differentiate exponential function? You still get exponential, right? Differentiate as many times as you want. 1 time or 2 times, you're still getting exponential function. So in this case, we will look for a particular solution in the same form as this forcing term. So in other words, we look for a particular solution in the same form as f, the right-hand side of this inhomogeneous problem. So y particular is going to be a times e to the negative 2t. So this is the form of the particular solution. Again, it's going to be similar to the forcing term, the one on the right-hand side, okay? It has to be in the similar form. All we did is we replaced the number in front of e by a, some a. So once you find a, you have your particular solution. All right, so I'm going to differentiate this solution, y particular, differentiate it twice, and then plug it into this equation. Okay, so let's take derivative. Please let me know if you agree, okay? This is the first derivative. This is the second derivative. Okay, so Do you agree?
Yes.
All right, thank you. We plug those into the equation, into the inhomogeneous equation, and from there we should be able to find A. So I'm substituting 4AE negative 2T minus, so now if you subtract negative, it's actually a plus, am I correct?
Yes.
Very good. And minus 2 times y, so that's AE negative 2T. So very good. What happens next? Next we cancel whatever we can cancel, and perhaps we can multiply both sides by e to the positive 2t. And finally find a, which is 1/2. So we have our answer. Our answer is y particular equals 1/2 e negative 2t. So this is our particular solution which satisfies the differential equation. Are there any questions regarding this example, 5.6? Any questions? So again, whenever you deal with exponential forcing term, you can use this method. It's called method of undetermined coefficients. This is the method of undetermined coefficients. And maybe we should write this down because it's this is the first time I mentioned it, right? So this method is called the method of undetermined coefficients. So the method used in example 5.6 is called the method of undetermined coefficients. Indeed, you're trying to determine a coefficient right in front of your e to the negative 2t. So this is why the method is called the method of undetermined coefficients. So we assume we know the general form of the particular solution. It's exponential. The only thing missing is this number. We don't know this number, this coefficient. So we substitute our general form into the differential equation and solve it for this unknown coefficient. So A in this problem is 1/2. Any questions? Okay, so let's practice with one more example. This time is the one, again, from the text. It's example 5.8. And we're going to consider all right, so here is the next, our next example. And this time, on the right-hand side, the forcing term is a sine function. What happens when you differentiate sine one time? What happens if you differentiate it one time? You're getting cosine, am I right?
Right.
And if you differentiate it one more time to find the second derivative, you're getting back to the sine. So derivative of sine is either sine or cosine. Again, this is the kind of situation which is very good for this method. So this method would work very good. So we're going to say our particular solution will have similar shape. So we're going to say, let it be A times cosine of 3t plus B sine of 3t. Did you notice that I'm using linear combination of sine and cosine? So again, our particular solution is not just sine. It's not A times sine of 3t. We have to take linear combination of both sine and cosine. And the reason for that is, again, derivative of sine is not sine, it's cosine. So you have to involve cosine into your particular solution. So from this point, we proceed to finding first and second derivative and then plug it all into the differential equation. Are there any questions?
Yeah, when you did cosine and sine, is that like the general formula when we derive something like that?
Right. So whenever you see the right-hand side is either sine or cosine or linear combination of both of them, your particular solution will involve both sine and cosine. So this is, again, the case when right-hand side is either sine or cosine or both.
Okay, thank you.
You're welcome. So again, it's your particular solution is not just B times sine of 3t. It's actually two terms, right? Linear combination sine and cosine. You have to write it this way, okay? So let's differentiate. Cosine is negative sine, so minus 3a sine of 3t and 3b cosine of 3t. That's the first derivative. And the second derivative is negative 9a. Sorry, yes, minus because we had minus over here. And I believe this is it. Do you agree with this?
Yes.
Excellent. So let's substitute all those derivatives into this differential equation. So y double prime okay, plus 2 times y prime, 2 times 3, 6 sine minus 3y and finally it's equal to 5 sine of 3t. So let me double check. So this is the second derivative plus twice the first derivative and then minus 3y. Well, let's see if we can cancel or at least combine some terms. I'm going to start with cosine. So I can see we have cosine, cosine, and cosine. And three terms that involve sine. So I'm getting a minus 12a plus 6b in front of the cosine of 3t. And then we have, all of these are negatives. So we have minus 9, so 12b minus 6a sine of 3t equals 5 sine of 3t. So let's double check. I'm combining again like terms, the ones with cosine, that would be minus 12a plus 6b I factored out cosine, and then minus, this should be plus over here, right? So 12b and then plus 6a inside parentheses sine of 3t. Well, do you agree with this? Please let me know. Yeah, I believe this is the same as in the text. So we're going to so let's see, we're going to compare left-hand side and right-hand side. So as far as cosine, there is no cosine on the right-hand side. So we will have to set this coefficient minus 12a plus 6b equal to 0. And I can see we have sine here and sine here. So this is negative 12b minus 6a will have to be equal to 5. So I'm getting system of two equations and two variables. Do you agree with this system?
Yeah.
Very good. Excellent. So from this point, let's use substitution. So minus 12a equals minus 6b. It's probably more convenient to divide by negative 6 and substitute this into the second equation. So I'm getting minus 12 times 2a minus 6a equals 5. So this is minus 24a minus 6a equals 5. So minus 1 over 6. This is what I'm getting for a. And b would be twice a. So b would be 2 times negative 1 over 6, which is minus 1 over 3. So these are the numbers that I'm getting. We're going to compare with the text. And yes, the text has the same numbers. So we're ready to write our particular solution. Let me do that here. So this is our particular solution. All I have to do is substitute minus 1 over 6 for a and negative 1 over 3 for b. Okay, and that's it. We're done. This is our particular solution for this example. So any questions? Any questions? All right. Example. So I'm going to try, I'm going to let you try on your own. Let me see what you say. This problem is tricky. I'm warning you, this problem is tricky. So try to find particular solution using the method of undetermined coefficients. So again, one more time, be aware, this problem is tricky. So I'll let you try. We had similar example over here, very similar example. Example 5.6, right? You also had exponential as here. So go ahead and try it and see, maybe in a couple of minutes, we'll return back to the main session and discuss this problem, okay? So again, we're going to have 3 large groups. Please join the room and discuss with your classmates, okay?